Hello, this is a workshop on causal graphs. And I'm going to try and make an argument that they will save us from the dangers of big data so that we can take advantage of them. And it's a very exciting time to be a linguist. There's more data out there and more ways to analyze them than ever before. And the next generation of big data methods even promise to create theories for us. But with great statistical power comes great responsibility. So there are problems with big data and we need to figure out how to avoid them. Here's an agenda for the workshop. So we're going to have some pre-workshop video lectures for you to watch. I'm going to cover what are causal graphs, a little on colliders, and colliders is an idea I really want you to take away from this. We're going to have some practice after that on identifying confounds using causal graphs. Then I'm going to go over some of the black magic of causal graphs in terms of causal axioms. Then how you would deal with real data, cover that very quickly. And finally, an introduction to SHIELD, which is a database of causal graphs for hypotheses in linguistics. So as we're going over these videos, if you have questions, note them down and bring them to the workshop, and we'll spend a little bit of time going over them. During the live workshop, then we'll have some practice coding causal graphs and using the language of causal graphs to try and understand people's theories better. And I'll send out more information about that soon. So, why use causal graphs? What the argument I'm going to try and make is that it'll help you do better research. It'll help you understand hypotheses. It'll help express your own ideas more clearly. It'll help you discover connections between work to design better experiments and to design better statistical analyses. It's a tool for helping you think. It won't magically solve your problems, but it is helpful, I think. So here's how I kind of think about things. Let's say we observe a correlation between the length of the word and its frequency. This is what we're interested in. Maybe we can come up with a causal explanation for that. But then we find that concreteness is also correlated with length, and it's also correlated with frequency. So we want to maybe control for concreteness when we look at the relationship between length and frequency. That kind of makes sense. But then we start to notice that many different areas and many different measures are correlated with all of these things. So things to do with acquisition, to do with neural structures, to do with interaction in face-to-face conversation, to do with contact between languages or emotions. Should we control for all of these things as well? And what's worse, all of these different things are also related to each other. So how do we turn all of these observations of correlations into a coherent explanation of causal relations between things? Because that's what we're really interested in as scientists. Despite the sort of hesitation scientists have about claiming that they have proved causal effects, really we are pursuing some kind of causal explanation in whatever work that we do. And it's getting harder and harder to integrate all of these ideas into a study. So we need some tools to help us do that. First of all, though, is this even possible? Let's ask Francis Galton. So he invented the correlation. He invented the idea of the cyclone and many other things, and had some very racist views. So I kind of think of him as the Iron Man of cognitive science. Powerful but slightly problematic. He could see that correlation doesn't imply causation. That's his sort of big contribution to science, and it's been a mantra for a long time. It stood for over 100 years, but then people like Pearl come along and say, hang on, wait, in fact, sometimes correlation in the absence of alternative explanations does imply causation. And if we think about causation carefully and about the ideas that we are trying to put together, then we can say something about causal relationships just from observations of correlation. So that's the big contribution that Pearl is. And I kind of think of him as the Captain America of cognitive science. This slide just shows you how old this presentation is. Anyway, what are causal graphs? Tools help us think. I'm just going to go over the basics of what they are. A causal graph is a mathematical language which helps us think clearly. They're most often portrayed in a graphical format as a series of circles with arrows. So sometimes people call the circles nodes and the arrows edges. And if you have two circles joined by an arrow, then the meaning of that is that if we were to manipulate x, if we were to change x in some way, then y would change in some way. That's what the causal arrow means. And then we have a third variable here as well. So this graph also suggests that if we were to change y, then z would change. And these kind of changes could be absolute changes, so it could be deterministic, or it could be statistical, probabilistic. It could be a sort of continuous change or a categorical change. And it's just a way of expressing an idea about how the world might work. I'm going to go into more detail about this in a second, but it's quite hard to think about these in abstract terms. So let's make this a little bit more concrete. I want to think about the difference between observing stuff and intervening between stuff, because intervention is a key idea in causal graph theory. So imagine you're walking along a beach and you see some people are eating ice cream, some people aren't. And you also notice some people have stains on their t-shirts and some people don't. And after a while you start noting down some of your observations. And you notice that more people have t-shirt stains if they're eating ice cream. And you start to wonder whether there's a relationship between these things. Well, first of all, what you're counting up is observations. And given this, you can look up the probability of, for example, having a t-shirt stain if you have an ice cream. So we can just plug in the numbers from that table and come up with a number. So you have an 83% probability of observing a stain on someone's t-shirt if they're eating an ice cream. But what we really might want to investigate is a kind of intervention. So what is the probability of a stain if we caused someone to eat an ice cream? If we intervened in their life and forced someone to eat, we ran up to them and we made them eat ice cream, would that cause them to be more likely to have a t-shirt stain? And in causal graph theory, this is noted as the do calculus. Let's see if I can get my mouse. In causal graph theory, this is referred to as the do calculus. So sometimes people write this little do statement. So there's the probability of a stain given that you've intervened and made someone eat an ice cream. So these two things are different, and the intervention is much more like a kind of experiment, a randomized control experiment. That would be the ideal case. So we take a load of people, we force half of them to eat an ice cream, and then we record whether they have t-shirt stains afterwards. So that's the kind of gold standard that we're looking for. And the black magic of causal graph theory is that sometimes we can make statements about intervention just based on observation. But let's build up to that. So let's make a causal graph based on our observations. So we could hypothesize that high temperatures cause more ice cream consumption, and more ice cream consumption leads to more shirt stains. So here's a causal graph that represents that idea. Temperature causally affects ice cream consumption causally affects t-shirt stains. So this says if we manipulated temperature in a suitable way, ice cream consumption would change. And notice that the arrow doesn't indicate positive or negative relationship or necessarily a linear relationship. It's just some kind of causal thing, and we can add that information in later if we want. Note it also says something, at least one other thing. So this graph suggests that there's no direct link between temperature and shirt stains. So if we were to crank the temperature up somehow, shove people in a greenhouse, they wouldn't necessarily get shirt stains, except if they were eating ice cream. So there's no arrow directly from temperature to shirt stains. We could put one in if we thought that was how the world worked, but this particular graph expresses that particular idea. And the key thing to get is that this is just an idea, an expression of an idea. So for example, we could make a causal graph that ran in the opposite direction. And this causal graph says that if you were to give someone a shirt stain, that would cause them to be more likely to eat ice cream. Eating more ice cream would cause the temperature to increase. Now, that doesn't sound like a very good model of how the world really works, but it's a perfectly good causal graph. It's a perfectly good possible idea, a hypothesis. So we can use causal graphs as to express hypotheses without needing to say that they represent proof that the world really works that way. Okay, so let's have a bit of a practice in interpreting a causal graph. I was part of a project a while ago that recorded lots of conversations between people, and we were interested in when people initiate repair, when they say, huh, or what, or pardon, and get the person to sort of repeat themselves. And this was our basic idea about how that was done. And I just want you to have a look at this graph and see if you can express our ideas given this graph. What does each arrow A, B, C, D, E actually mean? You can pause the video and have a go at that now. All right. So maybe the first thing that you've got is actually quite hard to get the context just from this graph. You need to know what people are discussing. So what is parallel activity, for example? Well, it's when someone is doing more than one thing at the same time. So they might be having a conversation while also peeling potatoes or something. So this graph says that if you were to increase the number of speakers in a conversation, that would increase the amount of noise and also increase the amount of parallel activity that was happening. Both noise and parallel activity cause a change to the probability of a listener not hearing something. And if a listener doesn't hear something, that affects whether they will initiate repair. So note that there's no direct link between number of speakers and listeners initiating repair, except for the effect that it has on them not hearing. Now, there may be several other things going on that explains the initiation of repair. For example, not understanding. And we might not know whether someone really doesn't hear or whether they don't understand. It doesn't matter if we can't measure these things directly. This is just a way of thinking about the relationships between the concepts in our study. Okay, I'm going to introduce a couple more conventions that you sometimes see in causal graphs. So the arrows are the main thing. Sometimes you see this line with a bar, and that means that the two variables are not causally related. Sometimes it's useful to explicitly depict that. So for example, ice cream consumption is not causally related to being a fan of Marvel. You might also get arrows in both directions, saying that they both influence each other. They're sort of co-varying or correlated with each other. That's fine. You can have arrows going in both directions. You can depict cycles in causal graphs. If you do, that sort of breaks some of the assumptions of some of the useful tools that you can use later. But if that's how you think the world works, then you're very welcome to depict the world that way. And in linguistics, there are lots of these feedback loops, probably. Sometimes you get indicator variables. So, for example, being a Marvel fan is a latent variable. We might not be able to measure it directly, but we can get indications of whether someone is a fan of Marvel by whether they've watched certain films or whether they have certain possessions. So a line with a dot means that you can measure one variable by measuring another, get an idea of one variable by measuring another. And finally, sometimes you'll see a node with U labeled on it. And usually that means there are possible unknown causes, stuff we haven't thought about yet that might affect things. And they might affect multiple bits of these things. So in this case, we're saying, okay, we think that there's no direct causal relationship between ice cream consumption and being a Marvel fan. But there might be some unknown thing that affects shirt stains and being a Marvel fan that we're not sure about, but we might want to take into account. Final thing some people ask about is the ability to depict changes through time. So if you have two variables that affect each other over time, you would have two arrows going in either direction. But a way to get around this problem, that will be a bit more detailed, is to break up the variable into multiple nodes for each time point. So for example, in this case, we're saying that there are different time points, time point 0, time point 1, time point 2, time point 3. So these might be seconds apart or days apart or something. And variable 1 at time point 0 affects itself in the next time point. So then you can imagine having a second variable that does the same thing. And now we can express something like variable 2 affects variable 1, but not the other way around. So we have this sort of arrow of time going from left to right. And sometimes this is a useful way of depicting the processes that are happening. So that concludes the first video. If you have any questions, note them down and I'll answer them during the workshop. Thanks.